are the rails, the hundreds of thousands of miles of metal which span the United States, the basis of the newest concept in mobile retaliatory power, the launch pad for Mobile Minuteman. The Mobile Minuteman force is complementary to the hardened and dispersed force, employing the same three-stage, solid propellant, inertially guided intercontinental ballistic missile. It is armed with a thermonuclear warhead and is capable of immediate retaliation against its specific target. The missile consists of the re-entry vehicle, the guidance and control section, the third stage engine, the second stage engine, the first stage engine. Connecting the three engines are the interstage structures. Constructed of aluminum alloy, they serve as the connection between engines and provide a means of separation of the stages at burnout. The first stage engine is constructed of 6 ring forgings of high-strength, low-alloy steel sections. Specific areas are insulated with Buna-N rubber, molded plastic, mastic insulation, and high-density graphite parts. The solid propellant formula can be manufactured to give reproducible physical and ballistic properties. Trajectory is controlled by 4 movable nozzles. This stage delivers 10.5 million pound-seconds total impulse, carrying the missile to an altitude of 92,000 feet. The burnout velocity is 7,000 feet per second. The second stage Minuteman engine chamber is constructed of girth-welded high-strength steel forgings. The inner surfaces are insulated with a prefabricated rubber blanket. The polyurethane bipropellant is cast into the engine chamber in a 4-point star configuration. A high-impulse, slow-burning propellant is cast into the aft closure, resulting in a substantial increase in the volumetric loading of the engine. The second stage engine delivers 2.75 million pound-seconds total impulse, which boosts the missile to an altitude of 300,000 feet at a velocity of 14,000 feet per second. The third stage engine case is fabricated using spiraloy, a glass fiber and epoxy resin structure, which has a very high strength to weight ratio. A double base solid propellant charge is cast into the case in a modified slotted tube configuration. The assembled third stage engine is equipped with 4 movable nozzles and a thrust termination system to place the warhead in the desired ballistic trajectory. For a nominal range of 5,500 nautical miles, the third stage engine carries the remainder of the missile to an altitude of 700,000 feet. Thrust termination occurs upon the receipt of a signal from the guidance and control section. The guidance and control section provides signals for trajectory control of the missile through the thrust vector control nozzles, sequence of firing, stage separations, thrust termination, and arming the warhead. A stable platform provides a reference for the velocity meters of the guidance system. It also furnishes the basic missile attitude references for the flight control system. This is accomplished by the use of transducers mounted on the gimbal axes. Stabilizing information is provided by angular accelerometers located in the interstage between the second and third stage engines. A general-purpose digital computer is used to compare the velocity information against the system's magnetically stored program. This comparison generates signals which are sent to the nozzle control unit of the operating stage to correct the trajectory of the missile. At appropriate times, the system provides signals which ignite a charge in the circumference of the interstages, producing positive separation from the remainder of the missile. Simultaneously, signals ignite the next stage engine. After thrust termination and before separation of the third stage, the computer checks the trajectory and velocity. The warhead arming and fusing system is pre-armed if trajectory and velocity are correct. While the vehicle is in free flight outside the Earth's atmosphere, it may tumble slowly. However, inherent aerodynamic stability will right it before the high heating phase of atmospheric re-entry. Early in re-entry, the arming and fusing system senses a fixed value of deceleration to activate the thermal batteries. This supplies power to pre-arm the warhead and to energize the ground burst frangible fuse grid. A fall-off to 10 Gs after peak deceleration closes an accelerometer switch to complete warhead arming. After a preset time, programmed for range, heading, and altitude, the contacts of the timer switch close to deliver an airburst firing signal. If ground burst had been selected before launch, the airburst signal would not reach the warhead. Instead, the current flowing through the frangible grid would be interrupted during the crush-up at impact. This action produces a pulse to detonate the warhead on target. The re-entry vehicle, which travels during most of its trajectory in ballistic-free flight, has two prime functions. It protects the warhead from temperatures approaching 12,000 degrees Fahrenheit, and it detonates the warhead. Re-entry protection is provided at the critical nose surface by a cap of Avco-White honeycombed quartz heat shield material. The remainder of the re-entry vehicle is shielded with Rad-58, a resin-bonded quartz composite. Being materials that ablate at high temperature, both dissipate heat by liquefaction and evaporation at the surface. This, then, is the Minuteman missile, an intercontinental ballistic weapon capable of immediate retaliation against its pre-selected target. It is the same missile used in the hardened and dispersed system, with capability of being launched from a railroad car. To assure that the missile would retain its high performance characteristic under conditions imposed by the railroad environment, a program of vigorous testing of all parameters of the missile and ground equipment has been conducted. Testing of the complete missile, conducted under close laboratory control, has established favorable response to these environments. After integrating road, flight, ground handling, and static test information obtained under the R&D program, special rail handling features were designed, tested, and have confirmed the predicted response to the expected environment. Also, during the summer of 1960, the United States Air Force operated a test train over several different railroads. To evaluate communications, the test train was equipped with single sideband high-frequency transceivers, and results confirmed that control and monitoring of random movement is feasible. It was also confirmed that existing railroad sidings and facilities can be utilized, and that the railroad environment presents no human factors problems. Mobile Minuteman units will consist of up to 5 missile cars and the required support cars. These mobile units will move in a random fashion along the nation's rail system, while denying the enemy knowledge of the continuously changing deployment pattern. Destruction of this mobile force would require complete neutralization of the rail system by nuclear weapons, an uneconomical and impractical operation. Thus, Mobile Minuteman assures the maintenance of a strong retaliatory capability after a surprise attack. The Mobile Minuteman system also capitalizes on the existent multi-billion-dollar investment in the nation's railroad lines, contributing to a substantial reduction in the cost of the weapon system. The missile cars will carry the weapon in an integral strong-back enclosure, which protects and supports the missile in a controlled environment. This environment is maintained until a few seconds before launch. Other equipment in the car includes systems to erect, align, target, monitor, and sequence the launch of the missile. The power car provides the primary power to the entire mobile unit. Utilizing 4 diesel-electric generators, it contains a 2-week fuel supply and the required electrical switchgear. 1 generator acts as a standby, and any 2 can supply the power necessary to effect launch. The command car provides for operations and maintenance support of the mobile unit. Within the command and operations area are the commander's console and the operations officer's console. These stations are separated by a bulletproof partition. Doors to the area are secured with a combination lock. Also located in this car is the communications terminal equipment, which provides alternate methods of radio communication with SAC headquarters. Living accommodations are being engineered to provide a human environment suitable for a deployment cycle of 2 weeks. One of the living cars contains quarters, the commander's office, and a briefing room. Another car is devoted to living quarters. The cars have shower facilities, a large water supply, and a chemical waste system. The last car contains the kitchen, laundry facility, and dining area. The dining area is multipurpose, being easily convertible to a comfortable lounge for off-duty recreation. It also serves as a ready room during strategic alert. This car also provides for 2 weeks' food supply, jeep storage, and sleeping accommodations for the civilian train crew. These cars, then, form the mobile unit. After assembly at the mobile unit support base, the train enters its deployment cycle. A civilian locomotive and crew move the train as it proceeds in a random fashion from one pre-surveyed launch site to another, stopping for periods of strategic alert. Train movement and strategic alert periods will depend on the enemy intelligence cycle. Many secondary launch sites along the main lines will be surveyed. Thus, the mobile unit will never be more than 10 miles from any launch site in the event that the launch command is received while the train is underway. The primary launch sites are, wherever possible, existing sidings, which allows the mobile unit to maintain its strategic alerts without interference with normal rail traffic. Immediately after switching on to a primary launch site, guards are posted, and the civilian crew proceeds with the spotting of the train. After the train has been spotted, the commander orders the Air Force personnel to their missile erection stations. Perforated tapes containing the missile targeting information for the specific launch site are removed from the file, verified, and taken to the missile car's equipment room, and programming is begun. Concurrently, the missile car jacks are lowered to stabilize and partially level the car. The integral strong back holding the missile is erected, transferring the weight of the missile and the strong back structure to the launch stand. The missile car operator adjusts the integral strong back to its true vertical position and rotates it to the approximate missile target azimuth for this launch site. A gyro compass provides the basic true north reference for azimuth alignment of the stabilized platform. The operator sets into the twist autocollimator transmitter the angle between true north and the target azimuth. The azimuth direction is transmitted upward by a polarized beam of light and detected by the twist autocollimator receiver. The receiver is mounted within the autocollimator platform assembly and servos to null with respect to the transmitter. This transfers azimuth reference from the transmitter to the receiver. The receiver then transfers the azimuth reference to the stable platform. The missile targeting and control console reads the program and the fusing information from the punched tape. It enters the program information into the cold storage portion of the airborne computer memory, sets the reentry vehicle fuse mechanism, and verifies that the setting is correct. On completion of the targeting and fusing operation, a personnel safety control device is actuated and the car is evacuated. The mobile unit is now within 1 hour after arrival on a strategic alert basis, and the missiles can be launched at 60-second intervals by the command car. The status of strategic alert is reported to SAC headquarters by radio, and the entire unit remains in a state of readiness until further orders. Many safeguards are provided to prevent accidental or deliberate unauthorized launch. The commander has the ability to disable the unit completely as a protection against any overt or covert action to seize the unit and fire the missiles. This action can be taken at any time until first stage ignition. Launch disable action deactivates all missile launch capability for the mobile unit. This capability can only be restored at the mobile unit support base. Additional inadvertent launch protection is provided by the strong back, which will not open with improper launch sequences or procedures. A power cutoff switch on the operations console can also be used to terminate all electrical power in the missile cars in the event of fire or major equipment failure. Identification of fire or security violations in any of the tactical cars is provided by simple, secure, paralleled networks, which provide positive readouts on the command and operations consoles. If a launch command were received from SAC headquarters, the message would be authenticated.
Tango, Romeo, Alpha, November, Lima, Golf, Echo.
Then the trained commander would insert a numerical launch enable code and both he and the operations officer would turn their respective launch keys. The integral strong back would open and the first missile would launch toward its pre-selected target. To assure that the missile would launch in accordance with its program, the mobile unit is equipped with monitoring devices to report the operational status of the weapon system during deployment. Gross monitoring functions in the form of illuminated indicators are located on the operations console. Indicators advise the status of each missile and its car at all times. Automatic tests are run at prescribed intervals to exercise and check out the missile launch equipment. Safeguards against inadvertent launch remain in effect during these tests. If failure should occur, then a failure indication results, and the commander informs both SAC and squadron headquarters of the change in status. A maintenance man is alerted to investigate the trouble.
Attention, attention, all electronic maintenance personnel. Malfunction in missile car 4. Repeat.
After determining the gross area of fault from an indicating panel in the missile car equipment room, the failure is isolated to a drawer level using a special purpose portable tester. The faulty drawer is replaced with a spare and the equipment rechecked to establish correct operation. When the malfunction has been corrected, the missile is put back onto strategic alert. Again, SAC and squadron headquarters are informed of the change of status. Malfunctions of the missile will not be repaired by the mobile unit's military crew. Instead, it will be shut down for the remainder of the deployment period. The balance of the mobile unit will remain on an operational status. In the later stages of deployment, at the commander's discretion, the mobile unit may be returned to its support base as soon as any non-remedial failure occurs. When the train is scheduled to move, the guidance and control system is switched to the transport mode to protect the gyros, and the integral strongback is lowered into the car, the jacks are raised, and the train moves to the next selected launch site. At the end of the 2-week deployment period, the train is returned to the support base for an 8-hour turnaround cycle. The tactical cars are separated from the train and taken to the tactical area. Any malfunctioning car requiring more than 8 hours maintenance is cut out of the tactical car string. The personnel cars are taken to their service area and the mobile crew is disembarked. In the tactical maintenance area, general support maintenance is performed on tactical cars. Equipment is tested and calibrated, and the cars are returned to the assembly area and assembled with the personnel cars and a new military crew. The mobile unit, after 8 hours, is ready for immediate redeployment. Within the missile transfer building is the equipment to replace the entire missile or any section. In the event the re-entry vehicle is the malfunctioning component, it is replaced and the car returned to an in-commission status. The guidance and control section is also capable of removal and replacement, enabling the car to be quickly returned to an in-commission status. In the event any of the engine stages must be repaired, the re-entry vehicle is removed and sent to munition storage, and the engine stages and strongback are then transferred to the tilt fixture. The missile and strongback are erected. The strongback halves are exchanged for assembly harnesses while the missile remains erected and supported by the positioning stand. Next, the assembly harness is raised to the missile by the tilt fixture. When the harnesses are secured, the missile is transferred from the positioning stand to the tilt fixture and lowered. The missile is then loaded into a transporter and sent to the missile recycle facility. At this point, a complete replacement missile is mounted on the car, and the car can be returned to the assembly or a ready storage area. Repair of the guidance and control system is accomplished in a special repair area and returned to spare storage as soon as possible. Within the ground support electronic area will be the programming test set. This is a flexible device using information contained on perforated tapes to control automatically a predetermined series of tests. These tests are conducted at various levels on electronic equipment using the programming test set with appropriate adapters. Measurement results appear as a printed record of the test. All warheads are repaired and stored in the munitions facility, where they are immediately available as replacements. The mobile unit support base also maintains facilities for general car repair. It is a complete self-contained terminal, providing all necessary facilities to maintain mobile units in a minimum turnaround time, which, with the high reliability of the units themselves, will maximize the in-commission rate of the weapon system. Each mobile unit support base will service 2 squadrons or 20 mobile units. Tactical deployment of the squadron will be determined by SAC headquarters through various mobile unit control centers. Air Force personnel working in close liaison with the railroad arrange for dispatching of locomotives and civilian train crews to pick up the mobile unit at the mobile unit support base. Coordination practices will minimize interference with commercial rail traffic while effecting random deployment of the mobile Minuteman units. Commercial rail crews and equipment will also be used to move the mobile units to sidings at Vandenberg Air Force Base, where mobile military crews will undergo familiarization training cycles, including test firings of the missile. These configurations, these designs and procedures represent the mobile Minuteman operational system. Minuteman. Mobile, elusive, alert, accurate. Designed for deterrence of aggression by penalty of immediate and complete retaliation.